Well, we'll go ahead, I guess, and get started, assuming I can get everything loaded up. Oh, okay, there we go. Let me. All right. Dr. McCormick's leather vest. Uh, he he um, he didn't let me borrow it, so I would have worn it though. I would have. Of course, I can't quite get the hair.
If you mix him and Dr. Cusick together, you get Indiana
All right.
but instead of wings, he has a cat.
Okay. We're just going to go ahead and use this as our screen. I've got this double screen going on with this computer, and I don't really like it very much, but this is good enough for government work. Okay. So welcome to, what is this, I guess my fourth FE session this semester, and next week will be my fifth. So this is what we're going to do this week. We're going to do sort of a comprehensive review of all things mechanics that'll be on the FE. And this will be applicable for both the civils in the room and the mechanicals in the room. So I'm going to get this started. Sign-in sheet. So real quick, let me sort of just briefly go over what it is we're going to be talking about. And that's this. So we've got a series of topics to discuss, but primarily we're looking at statics, dynamics, and deformable, or mechanics of materials. I'll be perfectly honest, when I first arrived at Marshall University, this is the first time I ever heard the topic called mechanics of deformable bodies. I've always heard mechanics of materials or strength of materials, so that's what it's referred to. So you've got here the topics that we're going to look at. This actually comprises a sizable chunk of the exam. Now, I pulled these numbers from the civil set of specs. I'm not sure if on the mechanical exam these numbers are any different, but you know, for statics, you're looking at 7 to 11 questions on the exam. For dynamics, you're looking at 4 to 6 questions on the exam, and mechanics of materials, you're looking at 7 to 11. That's a fairly sizable chunk of the test. Now, over here on the right, you can see the breakdown of the particular topic. So, for instance, statics, we're looking at resultants, we're looking at equivalence for systems, equilibrium, looking at frames, trusses, things like that. Dynamics, looking at kinematics, mass moments of inertia, force acceleration, impulse, momentum, work, energy, power, all that stuff. For mechanics of materials, shear and moment diagrams, stresses and strains, deformations, principal stresses, Moore circle. You all probably know the drill. One of the things about this review that we're going to do tonight is I did my best to try and not, I guess, double up on stuff that I've already covered. For instance, it was actually a while back, actually. My first session that I did this semester was a session on structural analysis. And I did shear and moment diagrams, I did support reactions, I did things like that. I'm not going to do that stuff tonight because I don't want to just repeat the same material over and over again. If you've been to both, I want you to get as much out of this as possible. But at the same time, I want this to be valuable for the folks who didn't go to the analysis session. So I think I found a happy medium. We're going to start off with statics. Now, I've provided you all a series of handouts from the reference manual. I'm going to borrow this real quick. So this is the NCEES reference manual. If you've had my sessions before, you know that I've referred to this here and there in the sessions. You will not get to bring a hard copy like this to the exam. There'll be a searchable PDF. But I think it's a good idea to be somewhat familiar with it. And I've provided you the appropriate handouts for statics, dynamics, and mechanics of materials, the appropriate sections in this, and you have those tonight. To be honest, we're probably not going to refer to those directly. A lot of that's just sort of rote and fundamental, but there are some sections that we are going to specifically refer to, so there's that. So with that, I think I'm going to sort of stop with the introduction and just jump right into it. So our first topic is going to be statics, and we've got a number of, I think, pretty standard problems with that. So, problem 1, we're looking at force resultants. Problem 2, this is a pretty classic statics problem. This is a pulley problem. We've got a sign being held up by a cabled system. This is an equilibrium of rigid body type problem. We've got another equilibrium of rigid body type problem, but this involves friction. And then our familiar friend, the centroid. So with that, let's go ahead and jump right into it. We'll take it one step at a time. Now, forgive me if the technology decides to fail me. I'm going to do my best to ensure that it doesn't. Let's see what's going on here. All right, so there's my smart notebook. Let's delete all of this. There we go. Okay, let me change my settings real quick. That's not what I wanted to do, but hold on. Everything's all tangled up. Okay. All right, let's just go ahead and do this. This is sort of the calibration thing, and since this is my first time logging into this machine, it's asking me to do that. Okay. What the? What in the heck is going on? One of each? No, not those, Sorry. These are mine. All right. Give me a second. Almost there. All right, there we go. All right, I think we can get rolling. Okay, so problem 1, we have an eye bolt, and we have a number of forces that are being applied in a number of different directions, and we want to know what is the resultant of these forces on the eye bolt. And this is honestly just a very fancy Pythagorean theorem type problem. So let me copy and paste this image. Let's see if I can. There's that. Oh, that is rather large. Come on. Goodness. All right. So here's problem 1. Are you... Wow. Oh, what's that? Oh, it worked. Let's try this little alignment thing again. I did do it backwards. Yeah, it worked. That's the thing. Oh. Do not drink and derive, right? So do not drink and derive. There we go. All right. Finally. Problem 1. Okay, so we need to determine the resultant of forces on this eye bolt. Really what we need to do is just split this up into individual forces and ultimately split them up into their x and y components. So the first thing I'm going to do is number these. So we're going to call that force 1. We're going to call this force 2. Going to call this force 3. Going to call this force 4. And we're going to take each of these one at a time, split it up into their x and y components, add up all the x components, add up all the y components, and then it's a Pythagorean theorem from there. So let's just take them one at a time. So let's start off with force 1. All right. So we have our x component and our y component. So what is the x component of force number 1? 0. And the y component is 10. And I'm going to put plus 10, all right, to indicate that positive is going up. And it doesn't really matter as long as you're consistent. Actually, well, yeah, it doesn't really matter as long as you're consistent. I was going to say, since we're determining a resultant, ultimately we're just going to get a magnitude. Okay. Now, for force number 2, we've got a 3, 4, 5 triangle, right? So something like this. This is 3, that's 4, that's 5. Okay. So if I wanted to determine the x component, it would be 15 pounds times what? Would I use 3 over 5 or 4 over 5? Now remember, this is going with the vertical. So if I'm looking at the x, it'd be 3/5, right? The force is going more up than it is horizontally. So this is 9 pounds. Fy is 15 pounds. 4 over 5, that'd be 12. Think about it like this, okay? What if I had a force that was going like this, and this was 1 to 12? So it was really, really steep, you know? See what I mean? So the higher component would be the y, right? This would be, what, 12 squared plus 1 squared, like square root of 145, something like that. See what I mean? Yeah. Okay. Yeah. Okay. Everybody okay with this? All right, and I'm going to put a positive sign on each one of these to indicate positive, to indicate that they're both positive. In other words, we'll say that positive y goes up, and we'll say positive x goes to the right. Okay. Force 3. Now, we were given an angle of, what, 30 degrees? Now, that angle is being measured from the horizontal. All right? So, Fx is going to be 20 pounds times what? The cosine of 30 degrees. And Fy is going to be 20 pounds times the sine of 30 degrees. Now, I'm going to figure out which one didn't bring their calculator, and I'm going to ask them. I'm just kidding. Did everybody bring a calculator? There we go. That's right. Those are senior engineering students coming prepared. Did you bring a calculator?
We need it? I figured we got some people in here to use them.
Relying on others for your answers, right? No, I'm just kidding. All right, what do we got for Fx? And Fy, 10 pounds. Now, what I'm going to do is this, I'm going to say that this is positive, but I'm going to say this is negative. Okay, does everybody see why I'm saying Fy is negative? Makes sense because it's going down. All right? Do that over here. Okay. Now, for number 4, we have an angle of 15 degrees, but that's being measured from the vertical. Okay? So because it's being measured from the vertical, our trig functions are going to be flipped. Okay? So the Fx is going to be, excuse me, 15 pounds times the sine of 15 degrees. Or you could say cosine of, what, 75 degrees? You do that and that would work as well. right. So fx and fy, what do they come out to be? Okay, so 3.88. And then now what are the signs on those? Negative. They're both negative because that force 4 is acting that way and down. Okay. So now we've got each component. All we have to do is add up the individual x components and y components, and then it's a Pythagorean theorem from there. So I'll say Rx is the sum of all the fx's, which is what? So it's 0 plus 9. So here, I'll do this. So 0 plus 9 plus 17.32 minus 3.88. Everybody see that? $22.44 pounds. And I guess we should put a positive on that. Ry is the sum of all the forces in the y direction. So that's 10 plus 12 minus 10 minus 14.49. Negative 2.49. So ultimately that doesn't really matter, but the sign, because we're going to use Pythagorean theorem here in a second. But if you want, you could sort of think that the resultant probably acts somewhere about like that. That's our resultant vector. Something about like that. Okay. How do we determine R? We use the Pythagorean theorem. So Rx squared plus Ry squared is the square root of 22.44 pounds squared plus minus 2.49 pounds squared. What is R? What's that? All right. What does that answer? What? Say it again. D. And there you go. Is that font big enough to read? Can y'all see that? All right. Does anybody have any questions about this? Not too bad, right? Simple. All right. Any questions? All right, next one. Find the tension that must be applied to pulley A to lift the 1,200 Newton weight. Okay. Now the newtons really doesn't matter. I mean, it could be 1,200 pounds, it could be 1,200 kicks. It really doesn't matter. But what does matter is the relationship between this weight and whatever that tension is. So let's, because I'm lazy, let's copy that. You think I'm not artistic. It hurts a bit. Actually, it really doesn't, because I'm not. I am not artistic in the slightest. Okay. Problem 2. Okay. All right. So what we've got is a pretty classic FE style problem on the static section, and this is a pulley problem. And really what my advice is on problems like this is to just take each pulley one at a time and do a free body diagram of those pulleys. And once you do that, I think you'll see that this is not a very difficult problem. One of the things about these elements, particularly the strings, think about it, they're strings. So what type of forces do you think those strings or those cables or whatever you want to call them, what type of forces can they resist? Tension, what can't they resist? Compression. So if you think about that, a lot of this is pretty straightforward. So let's start off with a free body diagram of pulley A. All right, so here's pulley A, okay, and I've got a rope yanking on this with some tensile force, okay? Now think about it, this is a pulley, okay? So that rope wraps around that pulley and goes up like that, right? This is pulley A. Make sense? So if the right side of this rope is seeing some tensile force T, what is the left side seeing? T, right? In other words, if I go over here to this image, I got the same tension in that right there. Now, so far so good? Now help me out. In statics, we know that the sum of forces in y direction must be 0. So how much do I have going up? 2t. So what do I got to have going down? 2t. So I propose that this force right there is 2t. Simple, right? Let's keep going. Now let's do pulley B. Is there anything else going on pulley A? All right, so pulley B. All right, so very similar. Here's the pulley. Now, what I'm going to do is this, okay? Notice how I drew this in red, okay? All right? Because what I'm trying to do is represent that rope right there. That's that rope. What is the tension in that rope? 2T. So that rope goes something about like that. And there's 2T here, 2T there. All right? Same tension. So this is pulley B. All right? What has to go down? 4T. Make sense? So, why did I draw that in that color? Because I'm looking at a different rope. So if I look here on the pulley, is anybody colorblind? I'm serious when I say that. Okay, no, okay. All right. So what we're looking at here is this rope. So, okay, all right. All right. That's all the same rope, right? I mean, isn't it? It's all one solid piece, right? Everybody okay with that? So, now let's look at free body for pulley C. All right. So what do I have? I've got this. This is C. And I have a rope going like this. And I've made 2 cuts through that rope, you know. Remember, samurai sword and or lightsaber if you happen to be a sci-fi fan, right? I cut here and here, you know, right through each one. So this is 4T and this is 4T. So what does that make this right here? What does that make this? Let's do that. 8T. Sound good? So I'm talking about this rope right there, right? Now I want to look at a free body diagram of the block. Okay? So here's a free body diagram of the block, and what do we have going on? All right, here's the block. And how much does that block weigh? 1,200 newtons, right? What ropes are attached to that block? This one, say it again, 8T and 4T. So this is 8T. That's 4T, right? So I propose that 12T has to be
Boom.
this is statics. Everything sits still. There's no boom. I'm just kidding. Kidding. All right. That's a good question, and for this, we're not really considering it. But you're right. You know, technically, those forces aren't meeting moment equilibrium. So, but we're not really worried about moment equilibrium for a problem like this. Just force equilibrium. Okay. Any questions? Okay. All righty. Okay. So, we have a sign that has a mass, bless you. We have a sign that has a mass of 150 kilograms. Okay? Now, the sign is attached to the wall by a pin right here, and it's supported by a cable between here and here. And I want to determine what the tension is in that cable. Okay? Sound good? All right. So let's go through this. Again, I'm being lazy because I'm not artistic. Goodness. All right. Y'all still read that? All right. Now, just curious, what's the weight of that sign? There you go, times gravity. The mass of that sign is 150 kilograms. That is a very easy trick to throw on the FE, okay? That, you know, if you're going through and doing the statics, you might take that the weight of that sign is 150. And there's probably in those A, B, C, D choices a choice that is off by a factor of about 9.81. See what I mean? So it's something to think about, okay? That's a very easy, I guess it's a very cheap trick to make, but it is easy to deal with. All right, now, first thing I'm going to do is determine the length of AC, just because I'm going to need that here in a second. Okay. What's that? You're right, yeah, because I was going to say this is that's the 3 side, that's the 4 side, and that's the 5 side. So if you want, you could use Pythagorean theorem or however you want, but it ends up being 2.5 meters. And if you want, you could say square root of 1.5 squared plus 2 squared. If you didn't see that, no big deal. You'll see where that comes here in a second. All right. Now, what I'm going to do is I'm going to sort of re-idealize this as follows. So I've got, you know, some sign, and it has a force going downward of 150 kg times g going down, okay? So that's going down, and I have, let's see, a hinge right here, okay? Instead of drawing the cable, what I'm going to do is I'm going to look at the equilibrium of this sign, and I'm going to say that right here I have a force going like that. Make sense? All right, so we'll call this force AC. And what I'm going to do is I'm going to split that into its x and y components. So this is AC y Oh, got ahead of myself there. This is force AC X. Fair point? Now, if you remember, and this is very similar to when you do a truss analysis problem, those X and Y components, they act completely along that line of action. In other words, if I'm looking at the sign, I can say that that X and Y component is here. I can say it's here. I can say it's here. I can say it acts anywhere along that line. Make sense? What I'm going to do is I'm going to move those right there. Right there and right there. See that on the sign? And the reason why I'm doing that is because if I want to, let's say, I don't know, some moments at B, the X component goes right through it. All right? Now, I think just about everybody in here has seen how I sum moments. I draw the little table, and I say everything spinning that way has to equal everything spinning that way. So if I sum moments at B, okay, what do I have going on? So you can look at my free body diagram. Well, the first thing I've got is the weight of the sign, right? Make sense? So I've got that 150 kilograms times G. Now, if this is point B, okay, so I'm at point B, here's the sign is spinning like this, right? In other words, if that cable is gone, that sign would go, whoop, 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 go like that, right? Well, actually, just sort of go like that. So we've got 150 kilograms times G times what, 2 meters? Assuming that that's right through the center of that sign. But I also have FAC Y, right? Acting at a distance of 2 meters. Make sense? Everybody okay with that? So the 2 meters are going to cancel, and I'm going to get that FAC Y equals 150 kilograms times G. And you engineers know what G is, right? That's the sound of my heart breaking. I'm kidding. For the folks listening to the recording, he's laughing. So he does know what G is, and I'm going to make him tell me what G is right now. There we go. He said 9.81 for those of you listening. I got to have fun with it, right? Units. Good sir, units. I'd argue that the number one thing that probably trips people up on this exam is units. Yeah. All right. Or one of the number one things. What does this come out to be? 1471 what? 0.5 newtons. There we go. All right. Excuse me. Now, the reason why we computed the length of the cable as a whole is because of this. I propose that we can use a very simple slope ratio, and we can say that the y component of that force is to 1.5 meters as the resultant is to 2.5 meters. In other words, this is just trig, really. I mean, how do you take, if we're looking at sines, what is the sine? It's the opposite over the hypotenuse, which is basically what I got going on here. In other words, if I want to find FAC, it is FACY, 2.5 meters over 1.5 meters. Make sense? What does that come out to be? So what's the answer? B. And a lot of times you'll find that the choices given in problems like this, like you won't see 2452.5. You'll see 2450. Most of the time on the exam is not really trying to do, what are the choices? 2450, 2451, 2452, 2453. Then it's not just a matter of whether or not you generally get the right answer, but you've all got to carry the significant digits and all that. That's not really what the exam's trying to test you on. I mean, the answers given for a problem like this were far enough apart that you could easily discern that that's the answer. Does that make sense? All right. Everybody okay with this? Okay. Okay. It's getting a little crowded up here. Get that out of the way. Okay. What's that?
Frictionless pulleys are very expensive.
What? The what?
Frictionless pulleys are very expensive.
Frictionless pulleys are very expensive. All right. So we've got a 100 kilogram block that rests on an incline. The coefficient of static friction between the block and the ramp is 0.2. Now the mass of the cable is negligible. We ain't got to worry about that. And the pulley at point C is frictionless. What is the smallest mass of block B that will start the block moving up the incline? And we got a number of choices. Okay. This is where free body diagrams come into play, and they are incredibly important. Okay. Hold on. Oh. Okay. All right. Now, before we go through all this, we might as well go ahead and get a weight of that block, which is going to be what? 100 kilograms times 9.81 meters per second squared. And that comes out to be 981 newtons. All right. Sound good? Okay. Now, let's test my artistic abilities. All right. Let's do a free body diagram of block A. All right. Okay. What?
This is straight line.
Okay. All right. Let's see what's going on here. Okay. So here's this block. Okay. Now we need to start adding some forces to this. Now, one of the first things I'm going to add is this. Now I'm going to say that this is W sub B. In other words, here's the block, and there's going to be some force pulling this, and it's going to be the same force as what's ever coming down here. Make sense? Sound good? Okay. Now, keep in mind that this block is going to have some downward force that we're going to call W sub A. Make sense? Now, ultimately, we really don't care about W sub A. What we care about is this. We're going to call this F sub n. Okay? And that stands for the normal force. Sound good? All right. Now, I propose that if this is a 3 to 4, right? If this is a 3 to 4, then I propose that this is a 3 to 4 with the slope ratios reversed. Can you read the slope ratios? Okay, all right. All right. In other words, this angle is the same. All right. Sound good? Okay. Now, we're going to have two more forces that's going to be acting on this. Okay? The first is this force right here, which I'm going to call the horizontal force at A, and then I'm going to call this the frictional force. Make sense? In other words, this block is normally going to want to slide down the incline, and the friction is what's going to keep it up, keep it sitting there. Okay, make sense? This FHA, what's happening here is this block is sitting on the incline. Gravity is pulling the block directly downward, but because the block is sitting on an incline, that gravity load is being split into an XY component. Does that make sense? Okay. All right. Now, let's deal with these horizontal and vertical components. Okay. Now, the horizontal component at A, we're going to say is the weight of A times 3/5. Now, why am I getting that? Well, I mean, you can just sort of think of this. I've got this block sitting on this incline, and it's, you know, think about like this. What if it was like that, and this was 1, to 12? It would have a very tiny, horizontal, or a very tiny vertical component and a very large horizontal. All right, make sense? All right. So this comes out to be, what is that? 981 newtons, 3/5. That comes out to be, what is that? Make me want to do a little bit of work. 588.6. Now, the vertical component of A, the vertical component along that incline, is the same thing as F sub n. Anybody remember what that stands for? Normal force. There we go. All right. So that's the weight times 4/5. So 981 4/5, and that comes out to be, I think, 784.8. Is everybody okay with that, or did I go too fast on that? Am I good? Okay. All right. Now, how do we determine F sub F? There we go. The coefficient of static friction, mu. So that is 784.8 newtons, 0.2. Plug and chug. What was that? 156.96. Everybody get that? Good? All right. Why does this matter? Okay. What I want to do is this. I want to sum forces in the x direction. Now, what I mean by that is this. I'm using the ramp as my coordinate axis. So this is the x-axis, that's the y-axis. Does that make sense? You see how I got that right there? Okay. So what do I got going on here? Okay, so going this way, I've got W sub B, and I've got F sub F, and then going this way, I've got F sub H A. Does that make sense? Everybody okay with that? All right. Okay. Let's see what's going on there. So W sub B equals F sub HA minus F sub F, which is, what do I have? 588.6 minus 156.96. Oh. What do we get here? Say it again. Newtons. All right. So, what do we do to this? Well, we're trying to determine what is the mass of that block. We know what that is, right? That's the weight of the block. So how do we determine the mass of the block? There we go. It was 9.81. What does that come out to be? 44.8? And 44 what? Well, there we go. Was it angstroms? You technically, yeah, I guess you could have just left it all in kilograms. But I wanted to be a little bit pure about it, and I think converting everything to newtons helps you remember that. Remember, your normal force times your coefficient of static friction will give you the frictional force that you have to overcome. It's like moving a fridge in your apartment. You know, fridge weighs X number of newtons or pounds. There's a coefficient of friction between the floor and the fridge that you have to overcome in order to get that fridge to start moving.
Out of curiosity,
Yes, sir.
if we were given coefficient of friction on the pulley,
Mm-hmm.
that's just going to be straight line. So you got tension going that way, but the friction force acting opposing that.
Well, that's a good question, and what I would say is the easiest way to get around that is to do this, is to do a free body right here. And if you do a free body, what you're going to get, here, let me sort of, if you do a free body there, what you're going to get is this. You've got, here's your pulley, right? You've got some force right here, and then off that pulley, it's going to be some force minus whatever you lost due to friction. And then it's just equilibrium to figure that out. Make sense? That's it. Well, I mean, also, let's not forget there's a arm there that's keeping it upright. So yeah. All right. Everybody good? This isn't too bad, right? See, this is simple. Okay. Now, last one. Our friend the centroid. Okay. So we need to determine the centroid of the following shape. Okay. Now, what's making this, I guess, a little complicated is the fact that there are holes in it. But this really doesn't make it complicated at all. A hole is just a negative area. That's it. Okay? So pretty straightforward. All right, so now, one of the things to note before we begin this, anytime that you do a centroid calculation, you must reference all of your distances from a common datum or a common coordinate system. In this case, that coordinate system is right here at the lower left corner. So when I start writing, sum of ax over sum of a and sum of ay over sum of a, all those x and y distances are going to come from right there. Okay, so we're going to need to be somewhat consistent with this. All right. I'm not. The program is. That was good. Well, it's like 7 o'clock at night, so I'm guessing none of them are in the building. All right. Okay. So let's take each of these one at a time. Okay. Let's do the y one first. Okay, and then we'll do the x one. Keep in mind, I don't think it's really going to matter. Okay, if you look at your choices, each choice. Here's another thing in terms of strategy. Let's look at this. Okay, this wanted us to find the x and y coordinates of the centroid. Now, if you notice, look at the answers that were given. Each answer has a unique x coordinate and a unique y coordinate. Do you need to determine both to get the right answer? Just do one of them. Okay. So let's do our vertical distances, and let's get y bar. Okay. So the way I do this is I strike myself a little table, and we'll start off by listing shapes. Okay. Now, this is how I'm going to do this. This is going to be my labeling. Okay. I'm going to split this up into 3 shapes. Okay. I'm going to say the rectangle, I'm going to say the square hole, and the circular hole. Make sense? Okay. Now the first thing we're going to need are areas. And I need to put that in square centimeters. All right. Now, help me out. What is the area of the rectangle, the big rectangle? 80. Now, what is the area of the square hole? 4. So, but since it's a hole, I'm going to say it's -4. All right. Now, the circular hole, how am I going to determine the area of that hole? So I can say the area of the hole equals pi over 4 d squared. So pi over 4 times 4 centimeters squared is what? 12.57, something like that. So we'll say negative 12.57. Now, here's what I'm going to do. I'm going to put a set of data here down below, and I'm going to put the sum. So I want to sum up what's going on here. What's the sum of everything in that column? There we go. Sound good? Okay. Now what we're going to do are y distances. Okay? Now what I want are vertical distances. So we take each of these one at a time. Let's start off with the simplest one, which is, I think, that hole. I want to go from this horizontal line here at the bottom, right there. I want you to tell me how far it is to right there. Simple, right? Make sense? And what is it? There we go. Okay. Now, that one's simple. Now, help me out. Let's do this one. How far is it to there? 2. How far is it then to, I don't know, maybe about right there? 5. Simple, right? Why do we need that? Because we need AY. So how do we do AY? A times Y, A times Y, A times Y. So what's 80 times 5? 400, right? All right. What is negative 4 times 2? What is negative 12.57 times 7? 7, was it 0.99, something like that? Okay. Now, I want you to sum all these up. What do you get? Like 0.01, something like that. Close enough. Okay. So Y bar is the sum of AY's over the sum of A's, which is 304.01, and the units are cubic centimeters, over 63.43, and the units are square centimeters. What does that come out to be? So what's the answer? What do we think? We are moving on up. And we are moving because our next topic is dynamics. Ha ha ha! That's a good question. What's next week? What I'm going to do next week are 2 topics. I'm going to do statistics, because we did not cover that, and I'm also going to do computer science.
Excel?
Actually, a little bit of Excel and some programming flowcharts. It's on the exam. It's on there. It's pretty basic, but it's on there. It's more like if I have a program, like a loop or something, and I put in x equals 4 and it goes through and does its thing, what's the answer? You will get asked that on the exam. No, it's not about code. That's not what it is. So, but the ideas you need to understand. I don't think it's like StarCraft. That was a pretty random reference. It's more like Diablo. I'm just kidding. All right. So a little bit of dynamics, okay? You're going to find that a lot of this stuff is pretty similar to what you did in physics, because that's really the kind of stuff you get asked on the exam. It's pretty basic stuff if you remember. Okay. So a particle starting from rest experienced an acceleration of 3 meters per second for 2 seconds. The particle then returned to rest in an additional distance of 8 meters. Assuming all the accelerations were uniform, what was the total time elapsed? Okay? So, let's just take this one step at a time. Okay. Okay. So let's start off with some basics. Okay. So this particle did two things, okay? The first thing it did is it started at rest and then it accelerated for a little bit. Then it slowed down. Does that make sense? So there were two events. Let's take each of these actions one at a time. Okay. Now, it started at rest, okay? So its initial velocity is 0, okay? Now, its acceleration is 3 meters per second squared, and it did that for 2 seconds. So I propose that its final velocity is its initial velocity plus AT. Y'all remember that? Bringing it back, right? All that basic physics. Been a while, right? In other words, if it accelerates 3 meters per second squared for 2 seconds, when it's all said and done, it's got a final velocity of 6 meters per second. Everybody okay with that? What's up? Yep. That's pretty fast. I don't think I can run that fast.
That'd be going all these tables in a second?
Close, yeah. That's about right.
Will can do it.
Yeah, but I think they're a little longer than a meter. What's that?
Will can do it.
You might be able to.
You want to race?
No. I will lose. Okay. Now let's look at action 2. Okay. Now action 2, what did it do? It slowed down, right? Okay. Now here's the point to make. Okay. It started off, it sped up, then it slowed down. Make sense? So its initial velocity in this phase is 6 meters per second, right? And its final velocity is 0. Maybe I should put 0 meters per second and meters per second here. Maybe I should be consistent with that across the board. Okay. Now, instead of telling us how much time it took to do this, it instead said that this occurred over a distance of 8 meters. Right? Now, remember this? Remember that? And if you don't remember it, that's what this is for. All right. Now, ultimately, what I want to solve for in this expression is what I don't know. And what don't I know in this? The acceleration. So I propose that to get that acceleration, it is Vf squared minus Vi squared 2x. So what is that going to give us? 36 over 16? Negative 36 over 16, I should say. So is that about negative 2.25? Now, does it make sense that the acceleration comes out negative? Why? It's slowing down. There we go. Now, why do we want the acceleration? Well, we want the acceleration because acceleration is the final velocity minus the initial velocity over the change in time. Right? Everybody remember that? Or time is Vf minus VI over A, which is 0 meters per second minus 6 meters per second over minus 2.25 meters per second squared. What does that come out to be? .67. So what's the answer? Say it again. 4.67, because this is how much time it took for action 1 to happen, the 2 seconds. This is how much time it took for action 2 to occur. So total time is 4.67 seconds. I did a little bit on that one. I know I said that these questions don't try and trick you, and then I tried to trick you. That was a little bit on me. What's that? It was just me. Dr. Curveball, yeah. I guess that's it. Had to let it out one more time. Right here, man. Right there. I'll have to come up with like some sort of Texas Roadhouse. Don't mention food. Goodness. Okay. All right. A 500 kilogram mass initially at rest is acted upon by the following force, expressed in newtons. What is the displacement at t equals 4 seconds? So this one's got a little bit more going on. This one's a little more involved. This one's breaking out the C word a little bit of calculus. Oh no! All right. What's that? There you go. All right. So our mass is being acted upon by the following function. Okay. So our force is 50 times the exponential of t. Okay. Now keep in mind that this is in newtons. Okay. All right. And our mass, which is 550, is in kilograms. So I'm going to be pretty fast and loose with the units since everything's already standardized. So when we express a velocity, it's going to be in meters per second. When we express an acceleration, it's going to be in meters per second squared. Everything's already put to the standard units. Now, if I've got an F and I have an M, what can I calculate from this? Acceleration. So to start, A is F over M, which is what? 50 times the exponential of t over 550, which is 1 over 11 e to the t. Sound good? Simple. Now, I've got an acceleration. What comes next? Well, I'm ultimately trying to determine displacement or position. Okay? Well, what's the relationship between acceleration and velocity? Let's start with that. Well, pretty much, yeah. Because acceleration is the derivative of velocity with respect to time. So therefore, if we want to find velocity, we just integrate. Make sense? What's that? Fun stuff, right? E to the t over 11 dt. Now, Luckily, I've been very nice with the functions here, because what is the integral of e to the t? E to the t. So the integral of this is e to the t over 11. What am I forgetting? Plus c. We're going to call this plus c1. You'll see why here in a second. All right? What's that? We are going to have to integrate again to get c2. It's sort of like deflections, double integration. But let's actually tie it to that. We're going to have two unknown constants of integration because we're going to integrate again to get position, which means we're going to need two boundary conditions, or in this case, two initial conditions. Okay? So where do we determine initial conditions from this problem statement? What two very, very critical words? At rest. So what does that mean when it says initially at rest? It means, what's that? At t equals 0, exactly right. So I'll call this initial condition number 1. At t equals 0, v equals 0. So that means that v equals e to the t over 11 plus c1. 0 equals e to the 0 over 11 plus c1. What's anything raised to the 0 power? 1. So 0 equals 1/11 plus c1. c1 is minus 1/11. There's one of them. So I can rewrite velocity as e to the t over 11 minus 1 over 11. Fair point? Sound good? Now, that's velocity. We're not quite there. What's next? Position. Now, how do we determine velocity with respect to position? Velocity is the change in position with respect to time. That's what it is, right? So I have velocity. If I want to determine position, I would say position is the integral of v dt, right? So it's the integral of e to the t over 11 minus 1 over 11 dt, right? Everybody okay with that? What's the integral of e to the t over 11? There we go, e to the t over 11. What's the integral of 1/11? 1/11th t, or t over 11. What am I missing? Plus c2. All right. We also have, to solve for that constant, another initial condition. At t equals 0, x equals 0. So x equals e to the t, what is that, over 11 minus t over 11 plus c2. So 0 equals e to the 0 over 11 minus 0 over 11 plus c2. 0 equals 1 over 11 minus 0 plus c2. There we go. Everybody okay with this? Am I going too fast or are you good? Okay. All right. What the heck? Okay. So therefore, x of t is the following. Et over 11 minus t over 11 minus 1 over 11, or fair point? Everything's divided by 11. Now, what's the question asking for? At t equals 4. So plug in t equals 4. So x at 4 is e to the 4 minus 1 over 11. So x to the 4 is what? I can do better than that. Okay.
Don't we have like a minute per question? Yeah. Pretty quick.
Keep in mind, these are meant to be challenging. These are meant to be a stretch. Oh.
Hey, you got a 25% chance to get one right.
Hey, there is nothing wrong with looking at your answer sheet and going, haven't guessed A in a while.
They take off. So they take off points if you just leave it blank too, right?
No, you get credit for correct answers. You don't get penalized for wrong answers.
Okay.
So answer everything. So, sound good? All right. Now, momentum. Okay, we got a 2-kilogram ball of clay moving at 40 meters per second, colliding with a 5-kilogram ball of clay moving at 10 meters per second. What is the final velocity if both of the balls stick together after the collision? Okay, so what do we got? Let's look at this. Oh, goodness. Back to the mathematics. All right. So, this is an exercise in the law of conservation of momentum. Now, does anybody remember how to compute momentum? Mass times velocity. Okay, so we've got two masses that are colliding. Okay, so we have mass 1 colliding with mass 2. Okay, now this mass has 2 kilograms, and it is traveling at a velocity of 40 meters per second. Okay, now it's colliding with this, going 5 kilograms with a velocity of 10 meters per second. Now, in order to be consistent, both of the masses are scalar values. Mass is mass. It's 2 kilograms, 5 kilograms is what it is. But in terms of velocity, I got one component moving that way, one component moving that way. So I'm going to take this term as negative. I'm going to say component 2 is moving with a negative velocity because it's moving that way. So I propose that the initial momentum is m1 v1 plus m2 v2, okay, which is 2 times 40 plus 5 times minus 10. All right? Plug and chug. What does that give you? 80 minus 50, 30. Make sense? Okay. Now that is the initial momentum going into this. All right? Sound good? What? Okay, all right. Now, this is initially what happens, okay? Now, these are two balls of clay. When they collide, instead of having two balls of clay, we're going to have, all right, so this is initial. All right, so this is initial up here. All right, when it's all said and done, and we look at the final scenario, we're going to have 1 plus 2 as a single unit, okay? So what is the mass of that unit? There we go. And what we're trying to find is the velocity. And we determine that by saying the initial momentum equals the final momentum. So therefore, the final velocity is the initial momentum divided by the final mass, which is 30 kilograms times meters per second over 7 kilograms. What do we got? That's it. What's that?
Can't remember, but I love it.
Everybody good? All right. Keep on trucking. Last one. Last dynamics problem. Okay. What's that? All right. We've got a child keeping a 1 kilogram toy flying horizontally by holding it on a string, going like that. The string is always in the plane of the circular flight path. If the plane flies at a speed of 10 meters per second, what is the tension in the spring? So what we got going on is this. All right. Okay, so this one's pretty simple. All right, all we've got is a mass of 1 kilogram, a velocity of 10 meters per second, traveling at a radius of 1.5 meters. Okay, so I'm trying to figure out where it is in the new manual now. So they've changed everything. Where is it? Okay, here we go. All right, so this is essentially centripetal acceleration, and your force component, I'm getting this from, I'm trying to, the formula is simple. It's just mv squared over r, and it's just plug and chug. 1 kilogram times 10 meters per second squared over 1.5 meters. And it comes out to be an answer in newtons, but I'm trying to find the formula in the book. I had it referenced, and then of course it changed.
What did you call this?
Centripetal acceleration. What's that?
Something about words.
Wait. I thought I had it. No, it's on there. It's just a. Oh, it's there.
If they took it out of the manual. Last action.
sue me for putting it on here.
Don't sue you too. Just sue everybody.
Good luck. I'm actually having a hard time finding it. I found a reference on normal and tangential kinetics on page 74, where your normal forces are mv squared over rho. So I guess that's it, but it was spelled out before. But, oh well. What does that come out to be? So.
Or you also call this tangential acceleration?
Yeah. I guess that's a fair way of putting it. But, alas. I mean, I remember the formula better than finding it in the manual, but it's pretty simple.
So just memorize all the formulas and we should get there.
Of course. All right. That's a good point to make. That's a good point. So the question was about the unit system, and I'll say this about the FE. The FE is primarily an SI system or an SI test. However, there are sections of the civil FE which are specifically U.S. units, namely my stuff, structural stuff, because all the code is referencing U.S. units. A lot of the structural civil stuff is going to be in U.S. units. Some stuff like this, where it's just kind of basic physics, it's probably going to be in SI. My mechanics and materials stuff that's coming up here in a second is all SI. You'll find some toss-up stuff here and there, like land surveying might be in feet and things like that. But you'll also find a lot of topics on the FE where the unit system doesn't really matter. Because let's say you're doing a differential leveling problem in land surveying. It doesn't really matter if it's in feet or meters. It's the same process. It's all numbers. Exactly. The same thing's true, honestly, with statics, like support reactions and structures. It didn't matter if they were kips or kilonewtons. The process was the same. So I just keep it in kips because that's what we do with design. So, okay. Everybody good? All right, we got one last topic, and I designed these problems to try and cover as much stuff as possible, okay? So I've got an axial problem, I've got a torsion problem, a shear problem, a bending problem, and a Mohr circle. So let's start off with the axial problem. So I have a 10 kilogram axial load. Keep in mind that's kilograms. I'm going to have to convert that to newtons. It's being carried by an aluminum alloy pipe with an outside diameter of 10 centimeters and an inside diameter of 9.6 centimeters. The pipe is 1.2 meters long. Young's modulus is 75,000 megapascals. Neglecting the effects of buckling, how much is the pipe compressed? And we have a series of answers. Okay, so this should be pretty straightforward. So problem 10. Okay, so let's start off with the axial load. The axial load is going to be 10 kilograms times 9.81 meters per second squared, which is 98.1 newtons. Everybody okay with that? All right. The length of that segment is 1.2 meters. All right, sound good? All right. Now E. E is 75,000 megapascals. Now, when in doubt, what I always suggest is convert everything to their base units. So newtons, meters, pascals. And the easiest way to do that is to recognize that this M is basically a short way of saying times 10 to the 6th. It's what M is, okay? So this is 75,000 times 10 to the 6 pascals. Sound good? Now, what we are going to need is the area of that pipe. Now, we have a pipe that looks like this. All right? It's the best you're going to get from me. That is 10 centimeters or 0.1 meters. And this is, what is that, 9.6 centimeters or 0.096 meters. Everybody okay with that? So I propose that to calculate the area of that pipe, we just take the area of the big circle minus the area of the little circle. So it's pi over 4 d naught squared minus di squared. So that's pi over 4, 0.1 meters minus 0.096 meters. And this is going to come out to be a really small number, so you're probably going to want to keep it in scientific notation. What's that? 6.157 times 10 to the minus 4 meters squared. Sound good? Huh? 158. I mean, yeah. Okay, everybody all right with this? Now, if I have a bar that's being yanked on, does anybody remember what is the formula for axial deflection? PL over, there we go. Probably. All right, 75,000 times 10 to the 6 pascals times 6.158 times 10 to the minus 4 meters squared, all under 98.1 newtons and 1.2 meters. So what does deflection come out to be? It's going to be small. Now, what are the units? This is a deflection. Meters. So, if I want, I can say 2.549 times 10 to the minus third millimeters. And how do I do that? I go 1, 2, 3. So yes, because the bar was being, wasn't being yanked on, it was being compressed. And now that should be right here on page 1, and there it is. Uniaxial on that second column, right on the top. All right, sound good? Now this next one we're going to be doing involves twisting, okay? And let's see, we're looking at page 82 to follow along because we're looking at angles of twist, Okay? So this is problem 11. All right. Okay, so problem 11. We have a steel pipe that is fixed at one end and it's subjected to a torque of 100,000 Newton meters. So this pipe is being twisted, okay? Now the pipe is originally 3 meters in length with an outside diameter of 35 centimeters and a wall thickness of 1 centimeter. Now steel has a modulus of elasticity of 210 gigapascals and a Poisson's ratio of 0.3. What's the angle of twist, okay? So we got a couple things we need to compute, all right? So this is a torque problem, so if you want, you can follow along on page 82. We have a torque applied that's 100,000 Newton meters, okay? Now, the length is 3 meters, okay? Now, where we're going with this is as follows. Ultimately, what we're trying to do is this. We're trying to determine the angle of twist, which for a shaft loaded in torsion is TL over GJ. So we're going to need two things. We're going to need G and we're going to need J. G is the shear modulus. Okay? Now we were not given the shear modulus, but instead we were given this. We were given... So, well, we're going to have to take a step. Which one? This one? You see it now? Okay. We're going to need to look at the shear modulus first and then look at J. Now, what you're going to want to do is turn to the very first page on your mechanics of materials page and look on the bottom left. Now, we were given an E of 210 gigapascals and a Poisson's ratio of 0.3. So how are we going to calculate G? There we go. So what does that come out to be? Did you not bring a calculator? I knew somebody didn't bring a calculator, so what's the answer? I'm messing with you. I'm messing with you. What we got? 80 point... I invaded your safe space. Is that what it is? I'm sorry. Now that's gigapascals, okay? Now, converting everything to base units, I'm going to say that that's 80.77 times 10 to the what? 9th pascals, okay? So convert everything to base units. Now we need the torsional constant. J. All right. Now let's see. If I had to guess, I think that's probably on the next page. Polar moment of inertia. Is that not on here? Did they not put this right with it? I mean, I know the formula. Let me see if it's in the statics. All right, okay. All right. This is where the hopping around comes in the manual. You got to love it. Go to the statics section, and I want you to turn to page 70. Plus, if it makes you feel any better, this is where Control F comes into play on the exam because you can search it. Now, do we see area moment of inertia in the big table on page 70? See for the pipe, what is it? Pi a to the 4th minus b to the 4th over 2. Everybody see that? Okay. What's that? I'm teaching deformable bodies. No, seriously, it's because I'm teaching it right now.
Some kind of robot.
He's something on a math position.
I don't know, though, with the way I was doing that tracing thing, me drinking and deriving, I don't know about all that. It was a joke, not really funny. All right. Okay. Now, what we need for this is the following, and this is where you got to pay attention a little bit, okay? Now, this particular pipe has an outside diameter. All right, so let's keep everything in centimeters for now. The outside diameter is 35 centimeters, and the wall thickness is 1 centimeter. So what's the inner diameter? Nope. 33. I see what you're saying, but yeah, 35, come in 1, come in 1. Make sense? So, A and B are the radii. So A and B are, so A is going to be 17.5 centimeters or 0.175 meters. B is going to be 16.5 centimeters, which is 0.165 meters. This is an exercise in unit conversion, let me tell you. All right. J pi over 4. Don't worry, it's going to come out to be a really small number. All right, pi over 2. Why did I put pi over 4? 0.175 meters raised to the 4th minus 0.165 meters raised to the 4th. Don't worry, it comes out small. Probably keep it in scientific notation. It's not what I'm getting. I'm making you do some work. My goodness. There we go. All right. So here's the formula. Our angle of twist is TL over GJ. We've got T and L we're given. There's G, there's J. Plug and chug. That's 10 to the 9th. T was 100,000 Newton meters, and the length was 3 meters. Now, if I calculate an angle of twist and all the units cancel, what's it coming out in? No. Radians. Big money, big money, no way me, no way me, no way me, no way me, stop. Wah, wah. Anybody get the reference? I like the show, I'm sorry, so deal with it. Showing my age. How old do you think I am? That's not an answer. What do we got here?
31. You're 31 years old. I don't even think it's 31 too. Like, I was supposed 28 or something.
I'm 29.
I was close.
You were close.
I thought about going 30 also.
You're a year older than Josh Poole. Is it with
I saw that.
Did you?
Yeah. Okay, all right, what do we got here? C. It's totally rad. All right. Three more. We're going to get there. All right. If we didn't have so much technical difficulty at the beginning, we would... Hey, we are in this together.
But we don't have to know how to do that.
I'm still saying we're in it together. All right. We have a beam with a triangular cross-section as shown. The beam is subjected to a uniformly distributed load of 80 newtons per meter, and the beam is 10 meters long. What is the maximum compressive stress in the beam? Okay, I've got my mechanical folks that are just kind of laughing. I think I get the inside joke. So, all right. So we've got a series of quantities. Notice how they're all in megapascal. The nice thing about this answer or this question is if we get the units in some level of stress, the way that SI works, everything's just a 10 off or 100 off or 1,000 off. So if we get the right numbers, we might not need to do a unit conversion at the end. So something to be said about that. All right. Now, for my structural analysis folks and structural engineering folks in the room, all right? Problem 12, right? All right. How do we determine M max for a beam subjected to a uniformly distributed load that is simply supported? We take WL squared and we divide it by... There we go. That's right. And if you don't know where I'm getting that, we have a beam that's like this. It's being subjected to a load like that. That's W. The beam is L long. So this is WL over 2. WL over 2. Shear diagram. We go up, go down, go up, so that's WL over 2 minus WL over 2, and that area is WL squared over 8.
Oh, yeah.
Our moment.
We should have had this a week ago. And then I wouldn't have failed that exam so bad.
If you open up your FE review packet at the end of the mechanics and materials section, is it in this one? I think it's in this one. Well, there's slopes and deflections, and then I think, well, these are slopes and deflections. These aren't moments, so, oh well. Yeah, right, yeah, it's in the structures. But you can do that. That's a pretty simple problem. So 80 Newton per meter times 10 meters squared over 8. So 80 over 8 is 10. 10 essentially cubed is 1,000 Newton meter. Sound good? Now, ultimately, this is a bending problem, so we're going to need sigma equals my over I. Okay? So we have a beam that is a triangular cross-section. So we need to figure out a couple things about that triangular cross-section. All right? So let's sort of pay attention to what's going on here. We've got a beam that looks like this, right? It is got a neutral axis that's probably somewhere about right here, right? That's the neutral axis. All right? Let's see if you all remember this. How far is it from here to here, and how far is it from here to here? Let's start off with the bottom one. Anybody remember this? H over 3. This is 2h over 3. Now, if you don't remember that, go to the static section. And it's funny how on page 69, there's a number of properties there, including properties for triangles. Now, we know that our extreme fiber distance, remember, if we're bending this and it looks like this is the side that's experiencing compression, right? So our extreme fiber distance, C, is going to be 2h over 3, which is what? 2 times 8 centimeters over 3, which is what? 5.33 centimeters. Everybody okay with that? Excuse me. Now, we're going to need the moment of inertia. So, okay, that comes from right here. All right, remember our bending stress formula? We measure from the centroid to our extreme fiber. You remember that? Okay. All right. Ultimately, what we've got is a bending stress profile that looks something like this. Okay, so here's our bending stress profile, and it does sort of that whole thing. And we measure that with my over I, where y comes from the neutral axis. So C is from the centroid to the way, 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 way tippy top of the beam, or the other way around to the way very, very bottom. Okay? So since the top is experiencing compression and the problem is asking for what is the largest compressive stress, I went to the top. Make sense? If it was looking for tension, we'd go to the bottom. Sound good? Okay. Now, our moment of inertia for a triangle is what? That's where the manual comes into play. In the static section on page 69. And since all of them are referencing from the centroid, it really doesn't matter which one you use because they're all the same. BH cubed over what? Moment of inertia of a triangle. Of a triangle, not a rectangle. You're looking for the centroidal one with respect to the centroid.
X or Y.
With respect to the x, because we're bending it as over 36. Now, how wide is this triangle on this problem? Yeah, this is B. Oh, I see probably what caused the confusion. You probably are like, how did he come up with a height of 8? Actually, yeah. This height is 8 centimeters. You're probably like, how in the heck did he come up with that? Watch this. All right. The bottom is 12 centimeters, right? Everybody okay with that? So would you agree with this? Would you agree that this is 6 centimeters and this is 6 centimeters? And this is 10 centimeters. This is 10 centimeters. So 3, 4, 5, or 6, 8, 10. Everybody okay with that? So somebody asked about area moments of inertia. I equals BH cubed over 36. There's an area moment of inertia. All right, so 12 centimeters times 8 centimeters cubed over 36 is what? Ends up being there's that. So therefore, bending stress is MC over I, or My over I. In this case, we're looking at extreme fiber, so that's C. So 1,000 Newton meters times 5.33 over 170.67. Bless you. Now you're probably going, wait, you're being a little sloppy with the units. Well, I am, but let's see what it comes out to be. What's the number? How in the heck did that work out? We can carry all the units out. Ultimately, though, it doesn't matter. Because what if it came out to be 312.3 or 3123 or 0.003123? It's a nice thing about metric, okay? All it is a matter of multiplying by 10 or dividing by 10 a number of times. Make sense? That's it. Next. 2 more. Everybody okay on this one?
1 minute, do 2.
B and C. All right.
Wait, really?
Maybe. Maybe not. All right. We'll get there, I promise. This is pretty straightforward. Okay. I did trick you with one fact on this problem. Okay? Let's look at this. A rectangular beam that's 4 centimeters wide by 6 centimeters high is being subjected to a shear of 7,000 newtons. The beam is constructed of 2014-T3 aluminum. What is most nearly the maximum shear stress? All right. Does anybody remember how to determine the shear stress in a beam? Does anybody remember that formula? Transverse shear stress? Page 82 if you don't remember. There you go. Now, I did trick you a little bit on this problem because V is the shear, Q is the first moment of area, I is the moment of inertia, and B is the beam width. So what fact in that problem is superfluous? No. Well, I can see where you mean it, but look at the text in the problem. What's the way out there statement?
2014 T3 aluminum.
Yeah, that doesn't matter. It could be made out of...
I ignored that anyway.
It's just a particular grade of aluminum. All right, so V is 7,000 newtons. Let's deal with the simple stuff. I is BH cubed for a rectangle over, well, there we go, which is 4 centimeters, 6 centimeters cubed over 12, which I'll go ahead and be nice and say that comes out to be 72. You're welcome. Now the width of that beam is 4 centimeters. Now, the only thing that's probably a little new or you can't quite remember what's going on is Q. Okay? Q is the first moment of area. So what do I mean by that? Here's the beam. All right? It's 4 centimeters wide and it's 6 centimeters tall. Okay, sound good? Would you agree that the centroid is somewhere about right there? Q is that area times that distance from there to there. So Q is going to be 4 times 3 times 1.5. Actually, what does it come out to be? Now the choice that you're selecting is 440 because the problem asks for what is most nearly the stress, and 440 is the one that's obviously the closest. Last one, and I promise you this one is incredibly plug and chug. All right, everybody got this? Okay. More circles. Everybody, are you still writing? Okay. All right. Given the following, what is most nearly the maximum shear stress? And again, this is one of those ones where units don't really matter because everything's consistent. Everything's all in megapascals, so it's all consistent. So we have a compressive stress along the x-axis, a tensile stress along the y-axis, and a positive shear stress. What's the maximum shear stress? Dependent upon our orientation. That's a very nice little plug and chug expression. So if you go to the manual in the mechanics section on page, give me a second. Say it again. 81. All right. So if you look on page 81, we've got everything related to, sorry, what am I looking at right here? Oh, maximum shear stresses. This is pretty straightforward. It's just a Mohr circle analysis. Okay. Now, the first thing that we're going to do is determine principal stresses, which is as follows. So we have sigma A and B, as they call it in the text, is sigma x plus sigma y over 2 plus or minus the square root of sigma x minus sigma y squared over 2 plus tau xy squared. Everybody okay with that? This is Mohr's circle. Everybody remember Mohr's circle? Oh, this is good stuff right here. Now, what I'm going to do is I'm going to say, all right, this term is called C. This term is called R. Why am I calling it C and R? Because this is where the center of the circle is, and that is the radius. Okay? Now, if you recall, before we start doing any math, we have our normal stress and our shear stress, right? We have, this is, sigma A, this is sigma B, and our Mohr circle looks something like that, right? So this term right there is tau max, right? But what's another name for that distance? R. That's the radius. This expression is the center, which is right here, plus or minus the radius. So if here's the center, plus the radius will put me here, minus the radius will put me there. So all I need is the radius. So tau max is, what do we have? Minus 140 minus 205 over 2 squared plus 100 squared. I know you all have seen that stuff before. I know it.
You doubt us.
No, I know it.
Where? What class? Who would have taught us this?
You learned it either in deformables or you would have saw it in soils. More cool?
Oh, we use it in soils.
We saw this in soils, yeah.
We maybe saw it in.
Oh, come on. I know I know Mr. Greer, he remembers
May
this.
have been watching Netflix. Or we may have
I remember you talking about it. I don't remember how to do it.
Oh, what do we get?
199.
And that is statics, dynamics, and mechanics of materials in one night. Before we leave, I know you all have been here for a while, and I know some of you are ready to go home, but does anybody have any general questions about any of this? I know this is probably one of those sessions that's really drawing upon stuff you haven't seen in a while, you know, and I understand that, so, you know, yes, sir.
Ask this question like most sessions, like what conceptual questions do you think?
Most of the conceptual questions that you can get in this section can come from actually a lot of stuff in CE 321, you know, like difference between elastic behavior and inelastic behavior, stuff like, you know, what is Poisson's ratio, the lateral strain to the longitudinal strain, a lot of stuff on terminology, and then just, I know this is going to sound pretty basic, but if I take a beam and put load on it, which side's in compression, which side's in tension, you know, where's the maximum stress, it's just stuff like that, basic stuff, basic fundamental conceptual knowledge. Does that kind of answer your question a little bit? Everybody good? One more and then I'm done. I will see you all next week. Not no more questions, but one more session. All right, we'll see you next week.